जी
So today we will do the fault level calculation.
जी सर.
So any idea about the quick calculation?
सर ये fault level calculation generally मतलब we generally take the जैसे कि like if two transformer is connected in parallel, how much fault they conclude in the bus. First we calculate the base MVA, and according to we calculate the percentage impedance up to the fault, and then calculate the fault current in general case.
So the same thing we will do here. It is a formula current. So current is voltage divided by impedance, correct?
Yeah.
If it is a three-phase, so voltage divided by rotary impedance. Same thing we will do. We will calculate the impedance and divide it with the voltage. Just 1 minute. Just 2 minutes. Hello? Yes, Rakesh, can you hear me?
Yes, sir. Sir, last we covered up to PT sizing. LA and we
Yes.
covered later. LA sizing or
The LA is not using the protection part. Okay, if you are asking, okay, so let me tell you that as
okay.
well.
Sir, your health is not okay, sir.
Okay, so LA to PT we have done. So LA means lightning arrest.
जी
Between phase to earth, correct?
जी.
So how we can size? The LA is just remember one thing. LA is size considering the maximum voltage. Suppose I am having a 33 kV system. So LA will be sized inclusive of the 10% of the value. Okay. So 33 plus that variation 10 will come 36.3. Okay. As it is connected with it will face to us, so I am dividing it with the root 3.
Sir, voice is very slow, sir, today.
Hello.
हाँ सर, now voice थोड़ी slow आ रही थी, सुनाई नहीं दे रहा सर.
अब ठीक आ रही है?
हाँ सर, जी सर.
So LA is basically sized considering the maximum voltage. Maximum means suppose I am having a 33 kV system.
जी.
So I will add the 10% variation, voltage variation. Okay. So
Okay,
which
sir.
is so it will come 33 into 1.1 is the 10% variation, so 36.3. Okay. As LA is connected between phase to earth, so dividing it with the voltage, dividing it with the root 3. So it is phase to earth. Okay. So divide with the root 3. Now
Okay.
peak voltage for the peak, it is a RMS value. So I will determine the peak value. So for the peak value, I will multiply with the root 2 times. Okay.
Okay, sir.
So LA for the R system will be 29.6. Means for the 33 kV I can use for the 30 kV LA. Same If I want to determine the 11 kV system for LA, so same thing will be done. 10% voltage variation plus root 3 times divided by the voltage and the peak divided with the peak value. So 10 kV LA.
Okay.
Okay. Now, suppose this is used for the earth system. Suppose our system is unearthed, then this voltage will be multiplied with the 1.4. 1.4 is the multiplying factor. So 42 kV LA will come.
Okay. Sir, in LA there is a discharging current is mentioned that 10 ampere for.
Yes. That is the discharge current. See, whenever the okay, let me tell you that part as well. Is the sizing part is clear?
Yes, sir.
That is called the discharge current. Okay, that this discharge current means whenever this is the value of the discharge current when the LA will work. Okay, this is the current flow from the ground towards the ground.
Okay.
Okay, it is the allowed discharge current when the LA will work. Okay, when the surge will come, and this is the energy which will flow in the ground. Okay,
Okay.
this is called the discharge current. This discharge current is having a general standard. If your system is less than 22 kV, generally we are taking it 1.5 and 2.5.
Yes, sir.
If your system is above 66 kV, so normal discharge current is 10 kiloampere.
Okay, sir.
Okay, so that's the general practice we are using, but it is not depending on the sizing. It is depending on the voltage only. Okay, if your system is less than 66 kV but more than 22 kV, then we can go for the 5 kiloampere. So this is just a discharge current.
Any
Okay.
timing is mentioned, sir? 10 ampere for 5 seconds. Timing is
No,
not
no, no,
mentioned.
no, 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 no. It's a current only. It's not a time.
Only current. Okay.
Yes,
Sir,
it's a current
one more
only.
thing regarding LA that in general, LA used before the transformer also. So there is a meter installed who indicates if green is then leakage current and is flowing and green, LA is okay. And if there is a red, then LA is not okay. So in normal case, the leakage current is flowing continuously from LA.
See, it's not like that. The LA means it is okay. Let me show you the picture first. See, this is my LA,
Yes, sir.
which is connected between phase to earth. See, LA is not allowing the flow of current in the normal condition. It will only this will only breakdown will occur. See, there is a what would I have? There is a chemical in this LA which will puncture only when the surge will come. Okay, in normal condition, this doesn't work. This LA.
Oh,
Uh,
okay.
okay, this will only work when the surge will come. When the surge will come, then there will be low impedance path uh, will be provided, and it will break down, and it will break, and then higher frequency will go towards the ground. Normal
Okay.
frequency it behave as a open circuit.
Yes, sir. So if LA operate one time, so it will be replaced or how many operation can be it can sustain?
How many operations? Oh,
Like how
oh,
many surges can be grounded to the LA?
that needs to be verified. It's no idea about this. That needs to be verified with the vendor. How many operation cycle? Basically, it is defined in the vendor catalog. How many operation cycle it can withstand. I don't think that we need to replace it in every cycle. Okay, let me check it with the vendor, then I can get back to you on this.
Because
Okay.
there is a counter meter also mentioned in the LA that
Yes,
uh,
yes. Unless the counter meter is there, it will only count how many times it will basically discharge. So this
yes,
can be used basically. We want to see how many discharges are coming. It doesn't mean that if the counter meter will showing the some counting, then we need to replace. Okay, there are some cycles are there which is verified with the vendor. Okay, no
okay,
need
sir.
to replace it every time. This is only for the counting thing because surge is a very important thing and it can damage our equipment. So just for counting it, we are using the counter meter. It
And
doesn't mean
what about this
we
leakage current?
लीकेज करंट कहाँ फ्लो होती है इसके एल के अंदर.
नहीं, जैसे कि एलए में एक मीटर लगा रहता है सर, एक्चुअली में वो ग्रीन और रेड दिखाता है, मतलब तो ग्रीन मतलब एलए इज हेल्दी और रेड मतलब एलए इज नॉट हेल्दी, मतलब ऐसा मीटर आता है.
एल के अंदर
हाँ नहीं, एलए के नीचे वो जहाँ अपन काउंटर मीटर लगाते हैं ना सर, तो वहां पर ही वो शो करता है कि एलए हेल्दी है कि नहीं हेल्दी, तो वो मिली एम्पेयर लिखा रहता है उसमें, वो ग्रीन डिस्प्ले दिखाता है कि जो निडल होता है
हाँ
उसका
सर. देखो देखो नॉर्मल कंडीशन में क्या है, एक तरीका ये कैपेसिटर ही बनता है. ठीक है, यहाँ से
अच्छा.
क्या है, ये मेरा हाई वोल्टेज है, ये मेरा लो वोल्टेज है. तो नॉर्मल कंडीशन जस्ट एक कैपेसिटर है. तो इस
हम्म.
हाई वोल्टेज के से हमारा कुछ ना कुछ करंट, लीकेज करंट एज ए कैपेसिटर फ्लो होती रहती है.
यस सर.
Means this is not the power frequency current. This is just a small leakage current which is flowing because of high voltage to the ground. Okay, if that is flowing means this portion is basically working properly. Okay, this is not basically grounding the high voltage, the 50 Hz frequency current. Okay, only the normal leakage current, which is basically the because of the phase to the ground. It will
ओके.
continuously
ओके.
because it is grounded. This you can see in the high voltage test as well. There's a normal leakage current is always flowing because of the phase to earth.
Okay. And sir, what is the difference? Because in yard we use the LA according to the voltage level of the line, if 33 kV, 132 kV. Generally in the building we cover the voltage like a copper type LA we used. So
Which
it
type of LA?
can sustain huge surges of that, मतलब जो लगाते हैं ना, 45 डिग्री कवर करता है LA जो लगाते हैं अपन.
वो तो बिल्डिंग की प्रोटेक्शन है, ये तो वो अलग चीज है. उसको
अच्छा.
इससे मत ये बेसिकली क्या है, वो तो क्या है, आसमान से तुम्हारी बिजली गिरेगी तो उसको
हम्म.
वो डिस्चार्ज करेगा. ये वो नहीं है, ये तो स्विचिंग सर्ज और लाइटिंग सर्ज का तुम्हारे सिस्टम में आएगी ना, तो तुम्हारे इक्विपमेंट
हम्म.
को प्रोटेक्ट करे, उसका इससे कोई लिंक नहीं है.
नहीं, वो तो ठीक है सर, लेकिन उसका भी कोई रेटिंग होता है या उसको नॉर्मल कोई भी कॉपर का
नहीं
एक
नहीं
लगा दो बस?
वो नहीं नहीं वो ऐसा नहीं. उसका उसका अलग से कैलकुलेशन करता है जो कि IEC 62305 होता है. इसके
अच्छा.
हिसाब से उसकी कैलकुलेशन करनी पड़ती है. उसका इससे कोई कोई लिंक नहीं है.
ये तो
तो
लाइन का
इससे
हो गया, वो ठीक है सर, आगे क्लियर हो गया.
क्या.
ये तो लाइन की रिगार्डिंग हो गया, वोल्टेज लेवल क्या है अपना, 132 है या 33
हाँ
केवी है,
हाँ,
और
ये
वो अलग
इलेक्ट्रिकल
अलग ही
ये वाला है बिल्डिंग के लिए.
जी.
फिजिकल डैमेज टू द स्ट्रक्चर एंड द लाइफ हैजार्ड, ये
जी.
अलग चीज है. उसका उससे कोई लिंक नहीं है.
ओके सर.
ठीक है.
यस सर. यस.
आगे बढ़े सर.
हाँ सर. यस सर, कंटिन्यू सर.
So fault level means the current means is we are dividing the impedance with the voltage, then we will get the value of the current. Correct. So I am just showing showing you one system. Okay, this is the grid from which this is the basic grid. Grid means I am getting some 33 kV supply from the grid. And after this, there is a transformer which is having primary voltage and secondary voltage, and also some impedance is there, which is called the percentage impedance. Percentage impedance is basically used for determination of the fault current.
Yes, sir.
Now, after this transformer, there are two motors are connected. So, like this, many system will be there in your company, and we can determine the fault current. The simple thing which I am doing is I am just calculating the impedance and dividing it with the voltage.
Yes, sir.
Okay. So first it is a grid. So from the grid I am getting the supply of 33 kV, and this is the fault current, fault MVA, which is coming from the source.
Yes, sir.
Okay. So how can we determine the fault level at this point? Root 3 VI. This is the voltage and current, and dividing it with the voltage. So this is the fault current which is coming from the source. Okay.
Yes, sir.
24. Now, the next thing is the source impedance. Source impedance formula is base MVA divided by fault MVA.
Yes, sir.
Base MVA is the transformer MVA, and this is the fault
Oh,
MVA. So 25 divided by 1500. Okay, this is the source impedance. Now I will add this with the transformer impedance. Transformer impedance, it is in per unit. This is also in per unit. So it is 8%. So I am adding both the impedance. So it is coming 0.0967 again in per unit.
yes,
Now
sir.
this per PU will be per unit will be converted to ohm. For ohm, this is the formula: percentage impedance divided by 100 into kV square upon MVA. Just to
Okay.
convert this in ohm, I equal to V equal to 3 Z. Z is
Yes, sir.
it in ohm.
Okay, sir.
Okay, so kV square upon MVA. So this is the same thing I have done here. This is kV square the secondary voltage ka square divided by MVA. Current will be V upon root 3 Z. E as the secondary side is response is kV. So divided
Yes,
by
sir.
root 3 Z. Okay, so this is the fault current which is coming from the source. Also, do you know the motor is also contributing to the fault current?
Yes, sir.
Because motor is having some residual voltage, so that will move towards the fault location. Suppose the fault will happen. Motor is having some voltage, right? Residual voltage. Suppose the fault happens here. So
Yes.
this will work on the as a zero potential. So fault the current will come from here, and also this is also at a higher potential. So current will come from here. So both current will be added. Correct?
Oh, okay, sir.
So suppose I need to determine the fault level at this point, then I will add the fault current contribution. Okay, so what kind of contribution is this contribution cannot be more than the motor starting current. So this motor is 560 kilowatt, so root 3 VI cos 5. This is my current, so starting current for the HT 6 times. For the LV, it is 7.2 times. And again, this is depending on the efficiency class of the motor. So you can make a thumb rule for the ST, it is 6 times, and LT, it is 7.2 times.
Okay, sir.
Okay,
But sir, in
so
motor case, motor is not a source, no, sir. A source of energy.
the motor is not a source of motor is in case of fault current. Yeah, in case of fault current, the motor is having some residual voltage. Okay, because
Okay.
of that, motor will rotate. So at that point, this will work as a source of energy, and it will basically backfeed the current from
Okay,
its
sir.
voltage. Okay,
Okay,
so
sir.
it is a source of energy when there is a fault. Remember, whatever equipment, all the equipment which are rotating in the nature are source of energy.
Okay, sir.
Okay, so rotating nature less like a motor, generator. So these are source of energy.
Okay, sir.
Okay, so we fixture is a source of energy. Light fixture. Suppose there is a light fixture is connected here. contribute to fault current?
Yes, sir.
Light fixture.
Light fixture.
Suppose there is any fixture is connected here.
Yeah.
So just tell me, will it be the source of energy?
I don't know, sir.
Anything which is having the rotating part, the light fixture does not have any rotating part, right? In the motor, there is a rotor and the stator, so it will rotate. So this will be
Okay.
the source of energy. Motor will be the source of energy. The fixture is not a source of energy.
Okay. Okay.
So I will add the contribution from both the motors. This is from the motor 1 and this is for the motor 2. So all the current will be added. So the fault current will be the fault current coming from the source and fault current coming from the motor. So this is the fault level at this location. Suppose I need to determine the fault current at this location. Then this impedance, transformer impedance, and the motor contribution and this cable impedance. All three impedance will be added, correct? And then I will add the motor impedance as well. So this impedance is this. So the fault current. Okay. So impedance up the transformer is this, correct? This is the
Yes, sir.
source impedance plus this transformer impedance. Now I'm adding the cable impedance. Cable impedance is Rx, which is the ohm per kilometer resistance value which I can get from the catalog. This is the reactance and this is the impedance. So R square plus X square ka under root and we will get the value of Z and this is the length. So it is coming 0.23 Z. 236. This is the cable impedance.
Okay, sir.
Okay. So all the impedance is added to this is the source impedance and transformer impedance, and this is the cable impedance. So both all the impedance are added. So the fault current value of the at this location is coming VF on root 3Z. Okay, 16.18. Now I will add it to the motor contribution. So the concept is clear. What actually I am trying to tell. Suppose I have to determine the fault at this location. So how many impedance are there? This grid impedance, transformer impedance, and the cable impedance. Right? These three impedance are there.
If fault is generating at the bus, the fault level
Which
is more, sir.
which which bus?
Bus 2.
Okay. Then here it is the grid impedance, transformer impedance, and the motor contribution.
And if the fault occurs at the motor terminal, then, sir,
Yeah. This impedance plus transformer impedance plus this cable impedance.
only cable impedance, na? And nearby
Cable
motor.
impedance, cable impedance plus this one. Or the source impedance. This impedance plus cable impedance, and the motor contribution.
But nearby motor will not contribute, and in this case, na, sir?
Yeah, why it will not contribute? It will be at the motor terminal, correct? So the motor will backfeed.
Okay.
Okay. Even if it is at the motor terminal, so this means it is at the zero potential. So motor will backfeed that current.
No, no. If fault is occurring at 560 kilowatt motor terminal, then
Yes.
800
Yes.
kilowatt motor will contribute in fault current or not, sir?
Everything will be contributed.
Yes, sir.
Okay. Every motor will contribute. All the motor will contribute because at the fault location the potential is zero, and all these motors are working on the higher potential.
Yes, sir. Okay, sir.
So all the things will contribute. So this will also be this grader will also be at high potential. This motor is also at the high potential. So I am adding both the motor contribution. Okay, 6 times for this motor and 6 times for this motor. So
Okay, sir.
the current will be added.
Yes, sir.
Okay,
So what
now
is
also
maximum fault current you written in last maximum fault
yeah,
current?
as per the IC 60909, just multiplied with the 10% margin, we will get the maximum value of the current.
But sir, something I read in one book, sir, कि if you calculate want to calculate the maximum fault level of any transformer secondary,
Hmm.
then just divide the rating by the percentage impedance of that transformer.
Yeah, this is the thumb rule. See, this is the detailed engineering, and this is the thing which you can calculate very easily. See, the thumb rule is divide the transformer current with the percentage impedance. But in this, you will not get any detailed study. Correct?
Okay, sir.
You will
Okay.
get the fault of the transformer only. This rule I also know. Determine the transformer current and divide with the percentage impedance. You will get the value of the fault current. But this, remember, this is only for the transformer. No other contribution is taken here.
Okay, sir. Okay. Okay, sir. Okay.
Okay, so this is a thumb rule. See, the fault current, we also required to add the motor contribution as well,
Okay, sir.
which we are not adding there. But anyway, we can utilize that.
Yes, sir.
Okay, now suppose these are the three DGs which are working in the parallel. So now tell me what will be the fault level on the bus 2,
Mm, sir, it will the summation of all the three, sir.
because the DG will work in the synchronization. So we need to calculate the fault current from the each DG. So how we can determine the current divided with the percentage impedance. Okay. So the my DG is, so how we can determine is MB divided by percentage impedance. Okay. Let me calculate. So fault MB will be, this is in the megawatt, correct? So I will first calculate the this is in the MBA. So I will multiply it. So I will divide with the power factor, correct? To get the MBA rating. Power factor is for the DTG is 0.8. Okay.
Yes, sir.
So base MB is also fault MBA is base MBA divided by sub transient reactance. Okay, so base MBA is 10 MBA or sub transient reactance 20% voltage 0.2. Okay.
Yes, sir.
Now the fault current will be just divided the voltage. Voltage is 6.6 kV. In case of DC, fault current will come very less. So it is 4.337.
Yes, sir.
Okay. 4.4. This is for the 1 DC. For the 3 DC, multiply by 3. 13.1 kilo. Clear?
Yes, sir.
So the same thing I am doing. I am dividing it with the current with the subtransient reactance only. So I will get the value of the fault current. Okay. Thumb rule is divide the current with the impedance, percentage impedance in case of transformer and subtransient reactance in case of DC.
Okay.
Okay.
So what thumb rule? What is thumb rule, sir?
Yeah, it's a thumb thumb rule. This thumb rule is also mentioned here. Suppose there are two types of thumb rule. Suppose I need to determine the 2 MVA transformer.
Yeah.
Then I will determine the current √3 VI. Secondary voltage is 415 volt, and
Yes.
then dividing it with the percentage in impedance. For the 2 MVA, 6.25 is the percentage impedance.
Okay.
So
Okay.
0.0625. So it is coming 44,517 ampere, and dividing it with the 1000, so it will come in the kilo ampere.
Okay, sir.
So it's a thumb rule basically. It's same for the DG. Same for the DG I'm doing. First, the thumb rule is divide current with the voltage, current with the percentage impedance. There is one more thumb rule is there. First, I will determine the fault MVA. So base MVA divided by subtangent reactance. So 7.5 divided by 20%. It is in MVA, so I will divide it with the voltage. It will come the current.
Okay, sir.
So the same thing can be applied here. Now, are you able to do this? This is a DC which is supplying the. This is the 11 kV DC which is supplying the power to this bus, and after this there is a 11 or 60 kV transformer. So we need to determine the fault at this location and at this location. So are you able to do this?
Yes, sir. At bus level, we will add the DG plus transformer both.
Which bus level? Yeah, this bus.
No, or bus A, sir. Bus A.
For the bus A, it will be the impedance of it will be the fault current coming from the DC and the motor contribution only, correct?
Motor. Yes, sir. Yes, sir.
Transformer is a static device. There is no rotating part, so there will not be any contribution.
Okay, sir. In that case, transformer impedance will not consider, no, sir?
Yeah. Transformer impedance will be considered only when the current is coming from here. So because of the step up and step down feature, this current value will change. So it will be added if we want to calculate the fault current at this point.
At bus B, we will consider all three: DG, motor, and transformer, sir.
Yes. We need to understand which current is basically contributing. Okay.
Okay, sir.
If
Okay.
we are able to understand this, then only we can find out the current correctly.
Yes, sir.
Okay, suppose there is a motor here. Okay, let me tell you. Okay, 66 kV, there is no motor is available. Now, just tell me what will be the fault current at this location when the bus coupler is off.
Grid and sir, this transformer will contribute, sir.
Grid transformer plus motor contribution.
हाँ sorry motor दिखाने सर motor yes sir grid transfer motor yes sir.
So this all will contribute. Okay. Now tell me when the bus coupler is on, then how much current will come?
Sir ये DG will also contribute मतलब DG contribution will add sir.
Okay, so both current coming from these sources, this grid transfer in the motor plus this DC will be also added. So it is a summation of the both the current.
So whenever sir we adding the more sources the fault MVA will increase sir.
Which MVA?
Like we
Fault current, yes, definitely fault current will increase. So we need to basically see the worst condition in our system. Whether are we operating BGN transformer simultaneously or not.
Yes sir.
If that is the case, then we need to add both the things because the current will be added. So the fault level calculation is done considering the maximum worst scenario.
Yes sir. Okay sir.
Okay.
Yes sir. Yeah.
Okay. Any question on